Okay, so exam results will be done, finished online before the end of the day tomorrow, and so they'll all be online, and I'll post an announcement on Blackboard. Watch your email for a Blackboard announcement, and then we'll talk about the multiple choice Friday, and you'll talk about the free response in your next recitation. Okay, if not starting Friday. Okay, so we're talking about parametric functions. Remember, this is a different type of function where we have this kind of behind-the-scenes independent variable, which we call the parameter, which is a different definition of parameter than we used before. Now, in parametric functions, the parameter is truly a variable. It's the independent variable, and it is both the independent variable for x and for y. There we go. Okay, magnetic field. All right, x equals, so this is 2 sine 6 pi t, and y equals cosine 6 pi t. So, is it a function? I had one yes and a couple no's. Is it a function? It depends. What are you talking about? Is y a function of x? No, y is not a function of x. But how is it a function? How can we think of this as a function, a valid function? Yeah, so ordered pairs are a function of t. Given a value of t, you only get one ordered pair, right? So choose a t, you're only going to get one and only one xy correspondence point. And so in that sense, it is a function. It's a ordered pairs x and y are a function of t. Okay, and so we talked about, and then what do you suppose this is? What do you suppose this is? Ellipse, right? So we've got an ellipse. This is 2 out here. This is 1 here. So maybe this is an ellipse. How can we prove it's an ellipse? Well, we would need to get it as a relationship of x and y to see if it matches that form of what we know an ellipse is, or if you remember. Okay? So how do we get a relationship of x and y? Solve for t and plug into the other one. All right, so let's think about that. Let's just think that through. I'm going to solve this for t. T is going to equal something with what? Arc sine. And then I'm going to take something with arc sine and I'm going to plug it into cosine. How's that feeling to you? It's not convenient, right? This is just not very convenient, right? And we know arc sine has this like limitation on its range, right? So it has a limitation on its range. It's only going to give values from negative pi over 2 to pi over 2. So this is kind of not convenient. And certainly we're not going to recognize that as an ellipse if we have the cosine of some expression of arc sine. We don't recognize that as an ellipse. So we need something different, okay? So in cases like this, when you start solving for t and it's getting ugly, right? And you're plugging in, we need something different. So we're talking about sines and cosines, so we want to make use of identities, okay? Instead of solving for t and substituting, we want to make use of identities to get rid of t. So any identities come to mind of sine and cosine that might help us eliminate t? Yeah. All right, so he said, so this should be a familiar identity. In fact, it's like the first and most important one. It's the Pythagorean identity. Sine squared of an angle plus cosine squared of an angle equals 1. So as long as the argument is the same, it doesn't have to be just a single variable. It can be, whatever argument you replace with theta. As long as you replace it in both places, sine squared plus sine squared of the argument plus cosine squared of the same argument will always equal 1. So do we have the same argument? Yeah, 6 pi t, right? In both cases we have the same argument, 6 pi t. And so we can take advantage of this. So we need to know, before we know what sine squared and cosine squared is, we need to know what sine is. What is sine 6 pi t equal to? Sine of 6 pi t. Right? Because we're going to eventually be using sine squared. So let's start with sine. What does sine 6 pi t equal? X over 2, right? X over 2. Divide both sides by 2. You get x over 2. And what does cosine 6 pi t equal? Just y. That's easy, right? So we're home free. If our sine, so we'll just do a little side work up here. If sine of 6 pi t equals x over 2, and cosine of 6 pi t equals y, then what is sine squared of 6 pi over t? What is sine squared? Or sine 6 pi over t quantity squared? What's that? X over 4? Yeah, that thing squared, right? So if I need sine squared, that's going to be that thing squared. So I can say x over 2 squared. Everyone agree that that's equal to sine of some argument squared? And then what is cosine squared of the same argument? Y squared. And look at that. My t's are gone. My t's are gone. And I got x squared over 4 plus y squared equals 1. And if you remember, you should recognize that as an ellipse, right? So an ellipse is x squared over a squared, so centered at the origin. So let's do it centered at any point. So do x minus a, I guess they do h. Okay, sorry, h. This is our equation of an ellipse. Where the center is. So the center is HK. And then, so with an ellipse, it's kind of like you have a different radius in the x and y direction, right? A circle has the same radius, but like it's kind of, ellipse is like a circle with a varying radius. And so the radius in the x direction, called the x directrix, is A. So what is that? So A is the x directrix, and B is the y. And again, these are like, this is like the radius in the x direction and the radius in the y direction. So what is our value of A here? 2, right? Because x squared would be x squared over 2 squared. And so does that agree with the ellipse we have? Yeah, this is 2, right? So this A equals 2. And what's the value of B? 1, right? So it agrees. So we've got, when we eliminated the parameter t using the Pythagorean identity, we got the ellipse where the x quote-unquote radius or directrix is 2, and that's x squared over 2 squared, and then the y is 1. Okay, so yeah, when you're dealing with ellipses and circles, we want to make use of the Pythagorean identity. We don't want to solve for t and plug it into the other one. Okay? Dealing with ellipses and circles, we're going to use Pythagorean identity as the means of getting the equation of the ellipse or the circle. Okay, and so what happens when A and B are the same? When A and B are the same, it's a circle, and then that's just the radius. And so then if we multiplied by that, say these are both a squared, if we multiply that, then we get the equation of a circle. X minus h squared plus y minus k squared equals r squared, which is the same for both of these, right? So when a equals b, we're going to call that the radius r, and the same formula for the ellipse becomes x minus h squared y minus k squared equals r squared. Right? Because if I divided by r squared, then I'd get a 1 over here. Over r squared, and 1. So a circle is just a special case of an ellipse, right? It's just a special case where the radius remains constant all the way around, right? Okay, let's look at another example here. Oh, so this equation and this function, same or different? So this equation and this original function that I have, same or different? Okay, how different? Okay, so t doesn't necessarily have to be time. We never said it was time. We could, often applications of these parametric equations have t as time, and so if, like you had a bug flying around or a particle moving, t would be time. But, right, and so what's the effect of that? The fact that we have this independent variable t here that we don't have here. How does that make these two things different? How does it make it different? Okay, let's see. So the only kind of rate of change we'll have here is like the rate of change of y with respect to x. So we have a rate of change here that we don't have here, right? So here we only have rate of change of y with respect to x, which would be like change. So it's, from this we can get dy dx. And that would be what, remember for Calc 1, implicit differentiation? We did implicit differentiation. We could get dy dx, and that would be, given any point, if you changed x a little bit, how much would y change? What multiple would y change of the change in x, right? But here, right, we've got rates of change with respect to t. So if you change t a little bit, how much does x change? So that would give us dx dt. And how much does y change? So we have different rates of change. What else is different? Yeah, Gabe. Mm-hmm. Okay, yeah, so it's good. So x and y is not a function. Y is not a function of x. We still have a function of t, but there's still one thing about this we haven't mentioned. This function. It's a big, important thing. Yes, sir? Yeah, right? So with t, there's a direction or orientation of the curve, whereas with x squared over 4 plus y squared over 1, there's absolutely no direction or orientation to it. Okay? So find the direction or orientation of the curve. Can you find it? Find the direction or orientation of this ellipse. What? And so that's with respect to increasing t, right? That's what we're talking. When t increases, how are the points generated, right? How are the points generated? Figure it out. Any way you can. Figure it out any way you can. Where's Robert? Robert Pereira. So just tell me your strategy. Don't tell me what you did, but how did you approach that to try to figure out the orientation of the curve? Okay, so for t. Yeah, so pick different values of t and see what happens. Now, you got to be careful with this one because if you do t equals 0, so let's do if t equals 0, what point do you get? Does anyone get that? 0, 1? Okay, very good. All right, so if you do pi over 2 next, 1, 0, 1 up here. Is that right? Okay, 0, 1. All right, so if you do pi over 2, what's going to happen inside this argument here? Really, what are we going to put into sign if we do, actually we don't, just like 1/2, right? So pi over 2 would be, we already got the pi there. So if I put in 1/2, thinking about pi over 2, what am I going to get for this whole thing then? I'm going to get 3 pi. And that's what? That's a whole rotation and a half around this thing, right? 3 pi is 2 pi is a 1 full rotation, so 3 pi is 1.5 rotations. So maybe that for the y coordinate, that'll put me down here. So that's not going to tell me what the orientation is because I just went around 1.5 times. So instead, we might want to try something. If we want to get pi over 2 out of this, we should do t equals what? We should do 1/12, right? So we need, because of that 6, we need to pick a real small value of t to actually see what's going on here. So if t is 1/12, then what point do we get? So it's going to be what? Sine of pi over 2 and cosine of pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So I'm going to have this point right here. So for t is 1/12, I just changed the argument by pi over 2. So that's a quarter of the way around, right? So when t is 1/12, I got my quarter rotation that I wanted. So now I can be confident that it was clockwise, right? Because t equals 0 is up here. T equals 1/12 is down here, this point 1, 0. So 2, 0. And so we've got what? Clockwise orientation. Clockwise orientation. Okay, did anyone approach it a different way? There's another way to figure this out. So this is kind of like the elementary way. This is kind of the elementary way. So now we're in calculus, right? So how can we use calculus to do this? We can use calculus to figure this out. Any ideas? Okay. Well, when I say calculus, what does it make you think of? Derivative, right? So let's take a look. What about dx dt? So when t equals 0, what is dx dt? Dx dt equals? So what's the derivative of that? You're here because you passed the mastery test, right? The coefficient will be, in the end, what will be out in front? Someone said 12 pi, that's correct. 12 pi cosine 6 pi t. Right? Derivative of sine is cosine. Chain rule is going to give us another multiple of 6 pi by the chain rule. Okay, so at t equals 0, that equals? Try again. 12 pi. Right? Cosine of 0 is 1. So we're going to get 12 pi. What does that tell us? So at t equals 0, dx dt equals 12 pi. Have a conversation. What is that information does that give us about what's going on here? At t equals 0, dx dt equals 12 pi. Talk about it. Go. All right, and then I'll give you a hint. Start off saying this. Given a small change in, you finish. Putting one word there will not make a sentence. Okay? Given a small change in, that's how you're going to start the sentence. But putting one word in there does not make a sentence. You're going to finish the sentence. Okay, half of you should be talking right now. Where's Jasmine? And Zuza? Jasmine, what did you guys talk about? Can you tell me about what does it mean that at t equals 0, dx dt equals 12 pi? Okay? She said given a small change in x, the change in y is 12 pi times the change in x. Griffin, agree with that? Okay? Okay, right. So good. He said, yeah. So you almost had it. You just were thinking of different variables, but right in the vicinity of t equals 0. If you make a small change in t, then the change in will be a 12 pi times as much. Like the change in x will be 12 pi times as much as the change in t that you pick. Okay. So given a small change in t, the change in x will be 12 pi times as much as that change in x, t. Is that a high rate of change or a low rate of change? Yeah, 12 pi is like over 30, like 38 or 40 or something, right? So yeah, 12 pi is like 38. What's that? Yeah, at t equals 0, right? So yeah, around t equals 0, near t equals so near 0, 1 when t equals 0. Is that what you mean? Okay, good, very good. Okay, and so right, so this is a very high rate of change. A little change in t means a lot of the curve is swept out because x changes a lot, right? X changes a lot for a small change in t up at the top. Okay, so how does that help us? So the original reason for this conversation was another way to find the orientation. How does this help us find the orientation? How does it give us the direction that it's going? Right, for a change in t, we get, it's 12 pi, positive 12 pi times as much. So which way is that change in x going to be? This way, right? It's going to be in the positive x direction. If our rate of change were negative, then for a change in t, we get a change in x in the negative direction. So the sign on that dx dt that is greater than 0 tells us going this way. And we wouldn't need to check 2 points. We just find the derivative with respect to t, plug in 0. Because the dx dt is positive, we know that the next point is what? To the right of the first one, right? To the right of the first one, because we got a positive rate of change. Okay, so there's the middle school way, plug in points, and then there's the college way, calculus, right? Okay, let's do another example. Any questions on that? Yeah, but I could have made. But what if y were sine and what if x were cosine? So it depends where. It depends relative to x and y. So you got lots of things. If you do something like that, you got lots of things to memorize then. So yeah, it's just for any given case, we just use the rate of change. Okay, here we go. Another example. This time, let's do. I will give you the equation of the ellipse, and you write the equation of x squared, so 16. This. Is that what I want? Okay, see if you can write the parametric version of this ellipse. Can you write the parametric version of this ellipse? Okay, so you're going backwards now. I gave you a hint. You need to make it look like this. If you can make it look like this, then you're one step away from writing x equals and y equals. Right? That's what we want. Parametric function. X equals a function of t. Y equals a function of t. Try one more minute. See if you can come up with it. Okay, where's Taylor Walton? Taylor here? Any progress? Okay, so what'd you get? 4x squared. Okay, good. And so what identity do we want to use? That's just like this, right? What is it, Taylor? Yeah, so what would that be? What is the Pythagorean identity? Okay, yeah, so, and let's use t's because that's what we want. We want cosine and sine as a function of t. Right, we've got 4x quantity squared plus y over 3 quantity squared equals 1. And we know we want to use sine t squared plus cosine t squared equals 1. And so this is what allows us to write what x is. So then what could we say x is to make this all be agreeable in harmony? Yeah, so you see that we can set for x equal to sine and set y over 3 equal to cosine of t. And that would maintain all of our relationships fairly, right? So then x would turn out to be sine t over 4. And y would be 3 times cosine t. So there's a parametric function that will give us what? This. And so that, can we sketch this? Sketch this. So we can sketch it. Maybe the easiest way to sketch it is using the equation of x and y. So what is our a and what is our b? So x squared over a squared. So if it's x squared over a squared, a would be 1/4, right? This would be x squared over 1/16. So a would be 1/4. And then b would be 3, right? So, right, x squared over a squared, y squared over b squared. So a would be 1/4, and b would be 3. So I need a new scale here on my axes. There we go. Okay, so so what does that predict? That predicts that, what? It's going to go by the x-axis here, 1/4 and negative 1/4, and the y-axis 3. Here's 3 and negative 3. So you can picture that. Now I'm going to put it in as the parametric function and see if that agrees. So what was our parametric function? 1/4 sine t and 3 cosine t. And it's, why didn't I get the whole thing? If you look over here, it's just graphing t from 0 to 5. To get the whole thing, I need t to go from 0 to not 6. 2 pi, right? 2 pi was a little more than 6. So if I do 0 to 7, that'll get all the points, right? I'll do 0 to 7. That'll show me all the points. Okay, so here's this ellipse. And so what's this? Find the starting point and the orientation, right? So find the starting point and orientation of this function. Go. I said it earlier. Can you say it again? Were they having trouble with that? Okay. Okay. Cool. Thanks. All right. Okay, what's the starting point? Meaning when t equals 0, what do we have? 0, 3. Okay, and the orientation? Clockwise or counterclockwise? You said clockwise. Agree with that? Yeah, it's actually the same thing we had before. X is positive sine, y is positive cosine. It's going to give us, what, positive cosine for dx dt. And so we're going to get the same thing as before. So let's take a look at this. When I went from this step to this step, did anyone do anything differently? Yeah. Okay. Yeah, so what about cosine t squared plus sine t squared equals 1? Is that valid? And so if I line things up with our equation, then what do I get? I get x equals 1/4 cosine t, and y equals 3 sine t. Different function, the blue function. Different or the same as the black one? Different function or the same? Let's see. Where's Ryan? Puskar? Where's James White? Not here? Where's Jacob? You're up. Different or the same, these functions?
They'd be the same.
The same. The exact same function.
Just they'd be oriented.
Okay, so what makes the function the same? So let's do the starting point for this one. T equals 0. What starting point do we get then for t equals 0 on this one?
1/4 for x and
1/4 0. So when I plug t is equals 0 into this one, I get 0, 3. When I put t equals 0 into this one, I get 1/4 0. Same function or different functions? They're different functions. If you get a different output for the same input, you're going to get, it's a different function. It's a different function. Okay? What is the same about them? There is something that's the same about those functions. What's the same about those functions? You're looking at it. They make all the same set of points, right? They create the same set of points, that ellipse. But how they do it is vastly different. And because of that, they're different functions, right? They're different. They do make the same set of same set of points. And that's how they're the same. They're different in the way that they do it. What's the orientation of this one? So we can come here and do dx dt equals what? Negative 1/4 sine t. At t equals 0, dx dt is 0. What's the orientation? Given that dx dt is 0, means for a change in t, what happens to x? It doesn't change, which should make sense out here at 1/4 0, right? For a moment, x is going to stay constant. What about the orientation according to dx dt equals 0? Is it going counterclockwise or clockwise if dx dt is 0? Can't tell. Either direction, you're going to have a pause in the x coordinate. Whether you're coming counterclockwise, x is going to pause. Or you're coming clockwise, x is going to pause. So this does not give us the information we want. What should we do? So dx dt didn't tell me the orientation at t equals 0. Do dy dt. Dy dt is 3 cosine t. At 0, dy dt is 3. Clockwise or counterclockwise? For a change in t, y is going to change 3 times as much as that change in t. Meaning, counterclockwise or clockwise? Counter, because dy dt is positive. For change in t, we're getting a positive change in y, which means up. That means we're going around counterclockwise. So not only do we get a different set, we get the points are not the same for the same t values, but then the orientation is different. That the first one, the black one, was clockwise orientation. This is counterclockwise orientation. Okay? Is there another way we can form this? Is there another way that we could do this? So we did sine equals to that, cosine equals to that, and then we did cosine equals 4x, and sine equals y over 3. There's actually more ways where all our relationships still hold. What's that? Okay, good. So that, all right, so another way is we could have a different argument, right? We don't have to, like we said before, we don't have to have just t. We could have sine of, say, a half t and cosine of a half t. And then this would affect the rate at which, so it would be the same if I did sine of, if x was 1/4 sine of, if x was 1/4 sine of a half t and y was 3 cosine a half t, we still get the same points, but what would be different? So let's do that. So how, the starting point will be the same, the orientation will be the same, but what will be different about the red function versus the black function? Volunteer, what will be different? Somebody new. Where's Christian? You Christian? Yeah. What will be different? Okay, so the rate at which points are generated, right? The rate at which points are generated. If we did dx and dx dt and dy dt, both of those would be half as fast as that one. So we're going to get all the same points, but with the red one, they're going to be generated half as fast, right? For a change in t, we're going to get half as many points as we did for the same change in t in the x one, because the rate of change is going to be half of each of those. Okay? Good. Still another way. I'm running out of colors. What about this? You might not think of this. So here's, I could say negative cosine t, positive sine t. Does that give me the same thing? Does that give me a valid result? And so what would x equal now? X would equal negative 1/4 cosine t, and y would be 3 sine t. Okay, so I want you to find starting point and orientation. Go. Starting point and orientation of that version. Where's Varun Mohan? How'd it go? Negative 140 at t equals 0. Okay. How'd you get it clockwise? How'd you get it? dy dt, you did dy dt, and you got 3 cosine t, which gives you, which is at t equals 0 is 3. And so then, keep going. So at this starting point over here, if y is positive, so we're at negative 140, if y is positive, clockwise or counterclockwise? Over here, going up on the left side of the ellipse means a clockwise orientation, right? So we got the same result for this part of it. Dy dt is 3, but because the starting point is on the left side, that means we're going up on the left side, and that means clockwise. All right, so given this ellipse right here, for any given argument, right? So one thing we said was we could change the argument. But for a given argument, there are actually 8 different ways to choose a sign, a plus or minus sign, and a plus or minus cosine, and arrange them. So there's 8 different ways, 4 different starting points, and 2 orientations for each starting point, based on how you use sine or negative cosine, or plus or minus sine, plus or minus cosine, and where you put them.